Hello everyone. This week our topic is going to be energy, but as I often do, I wanted to start off with something I call Chaco's math moment. Okay, so let's just put this over here. Chaco's Mr. C's math moment. Okay, let's see. And what we were going to talk about today is this symbol delta. Okay, because you're going to see this often. Delta. It's the Greek letter delta, and what it stands for is change. That's what it means. And it could be a change in anything. I gave you in class the story about how Mrs. C had me go pick up 12 donuts. And let's call those donuts D-O's for donuts. Okay, and I initially bought, initially meaning start, 12 donuts. And again, I stands for, the little I on the bottom stands for initial or starting. Initial. Okay, and I bought 12 donuts, as I said. She had me go to the Dunkin' Donuts store, buy 12 donuts, but on the way home, I realized there must have been a hole in the bag or something, because when I got home, my final count of donuts was now 9 donuts. So somewhere between the store and getting home, something happened and I only ended up with 9 donuts at home. Well, the change in donuts is equal to a donuts final, and F is going to stand for final, or the end amount. Let me just clean this up a little bit. I don't like the way that looks. Donuts final minus donuts initial. Now, in this case, we ended up with 9 donuts. But we started off with 12. So as a result, our change in donuts was equal to minus 3. That was our change. The bag that started off with 12 was now minus 3. And the reason I brought this up is I wanted to point out that the symbol delta could be used with anything. We could have delta time, okay, delta t, and I gave you a demonstration in class as to what that was. If we assume t to be time, and I'll just put t up here as time, then in this case the change in time would always be t final minus t initial. How about a change in distance? Change in d, where in this case d is equal to distance. Well, a change in distance would be equal to d final minus d initial. How about a change in velocity? There's another one. V for velocity. Change in v would be equal to v final minus v initial. Okay, so we got the point that a change in anything is equal to anything final minus anything initial. All right, and in our little example in class, we went on to talk about football games, okay? Because everybody seemed as though they could relate to a football game. Everybody kind of knew that if someone was on a 20-yard line, okay, if one team was on the 20-yard line, and they made this, what we call their, let's call it Y initial. Okay, and their Y final got them to the 30-yard line. Then the change in yardage, that's supposed to be a delta here. A change in Y would be equal to Y final minus Y initial, or this would be equal to 30 yards minus 20 yards, or a change in 10. But likewise, if the person had been pushed back from the 30-yard line to the 10, then our change in Y, let's assume they started off at the initial, Y initial here, at the 30-yard line, but then they got pushed back, their final yardage was to the 10, then their change in yardage would be equal to minus 10 yards. So you got to watch your signs very carefully. But if you keep it, the formula is always Y final. Okay, Y final here minus Y initial. And delta should be an easy concept to understand. You may recall also this week we talked about math formulas. Okay, so let's just put this up here. And I said it was kind of important to understand math formulas, and some key concepts that I wanted to talk about were these. Okay, so our topic was math formulas. And I used one formula, the formula for potential energy, which we will learn about this week. And I said potential energy was equal to mass times gravity times height. Now here's what I wanted to talk about. I told you all these letters in the formula, which I called nothing more than a recipe of how to mix numbers. I call these letters symbols. And I said it was important to realize that the symbols were used because no one wanted to write out all the time mass times gravity, which is an acceleration, gravity times height. And no one wanted to write out potential energy. It just took a lot of work and a long time. So they used letters M, G, and H. Well, these letters, this M, G, and H, we called, as I said, symbols. But they were not to be confused with units. Symbols were usually the first letter of what we were trying to symbolize. For example, let's write down symbols on this side, SYM if you don't mind. And I'm going to say this M was a symbol for mass. But the units for mass were very different than the symbol. The units were, let's use kilograms in this case. It could be grams or kilograms. And usually, kilograms had, the units had usually a number in front of them. Perhaps 3 kilograms or whatever. It could be any number in front of them. And it was telling you what the 3 was. In this case, the 3 was measured in kilograms. Okay? And mass was the symbol for that. So the symbols were used in the formula, as it says up here. Okay, the symbols were used in the formula, and the units told you what the numbers were in front of them. Okay, so let's do a couple more. Let's talk about, how about distance? Distance used the symbol D, but it was measured in meters. Okay, M for meters. And once again, you can see how the confusion could occur. M for the units, and for distance, but M for the symbol or for mass. So you've got to understand that when we're using formulas, all we're using is symbols, not units. Do not confuse the M used to identify mass, the symbol, with M, what's going to be used for meters. Okay, as the units for meters. The units for distance, rather. And just keep in mind, this could be any number. It could be 5 meters, 1 meter, 2 meter, 3 meters. There was usually a number up here, whatever it might be. Okay, no number in front of the M, unless it was part of the formula. I'll show you what I mean in a little while. Okay, so how about velocity? Now, velocity, let's skip a line. Do it in black again, just to keep consistent. Oops, black I said. Let's erase this. Velocity, as you can see, has a V in front of it. Okay. And its symbol was a V. Okay, there's a V. But its units were meters per second. And don't forget that also comes from the formula that velocity is equal to distance over time. Hence, distance is meters, the units. Time is in seconds. Okay, while we mention time, let's put time over here as another one. Time, T, had units of seconds or minutes. It could be minutes too, but so you can see, and my whole point is not ever to confuse the symbols used in a formula for the units used in the numbers that go in front of them. Okay? These units describe what the number is. 3 kilograms, 4 meters, 5 meters per second, 10 seconds. Okay, so you're getting the idea, I hope. And in our room, I pointed out a chart that showed you all the symbols that we were going to use and all the units. Just remember where that chart is, and I will continue to point this out all through your freshman year, making sure that you identify symbols and units and know the difference. You may recall that in class, I talked a lot about formulas and symbols and units. And I pointed out on the board, on the wall, a chart that showed you different symbols, different names, and what their units were. And I just want to make sure we understand this. I want to go over it one more time here. Force is defined as the push or pull on an object. Okay. And its symbol is F. In other words, in the formulas, let's show you what I mean. In the formulas, we use the symbols such that F is equal to mass times accelerations times acceleration. And you can see right here, F is the symbol for force. M is the symbol for mass. And A is the symbol for acceleration. Now, if you were to read a word problem, you might see the units right inside the word problem, and you would know that the word problem contains either a force, an acceleration, or a mass. For example, the word problem might say, what is the force exerted on an object with a mass of 10 kilograms if there is an acceleration equal to 5 meters per second squared. Okay, so you know we're looking for a force, F. Okay, you have a formula sheet which I will give you each time. You know that there is a mass, and it's 10 kilograms. Okay, notice the units, 10 kilograms, that the kilograms merely identifies what the 10 in front of it is. It tells you what this 10 is. It says that this 10 is in kilograms, which is equal to a mass. For the acceleration, it says the acceleration is equal to 5 what? 5 meters per second. Okay, that's an per second squared. That's an acceleration. So it's very easy to see, once you start to get the hang of it, what the units are and what the symbols are. The formula you would set up would be this formula right here. You'd be looking for a formula that has F is equal to mass times an acceleration, or F is equal to ma. So jot these down in your notebook as good examples of the name of different things we'll be using, the symbols for those things, and the units that go along with the symbols and names. The next thing we did in class, as you recall, was that we went over a few of the definitions that we'll be looking at as we go through Chapter 15. The first was energy. And don't forget, you should be comparing to the notes that you took in class to make sure you didn't miss anything. And I said the energy was the ability to do work. I also said there's another definition that you'll often see. And the other definition was work was the ability to move an object. Okay, so let's keep that in mind, and we'll try and see why in a second. Okay, we also talked about work. And we said work has a formula equal to force times distance. And just based upon that definition itself, you can see that there's two things that make work. You have to have a force and you have to have some kind of distance. So what does that mean? Work is the applying of a force. It is the applying of a force to an object that causes that object to move a distance. The direction the object moves must be the same as the direction the force is applied. So for example, let's draw a picture. Again, you know how great an artist I am, so I just love any opportunity I can to draw. And you'll recall that in class I had a chair. That's a chair. That looks like a chair, right? And of course the chair was sitting on our floor. And I applied a force to that chair. Okay, do you recall? Yeah, I'm not crazy about that picture. Let's see if I can do better than that. I had a chair. And I applied a force to that chair. And we're going to call that force F. But the first time I applied that force, I didn't push it. There was a force. I was bending my finger, but I did not push it enough to cause the chair to move a distance. Therefore, the distance was equal to 0, no movement. Well, if the formula says that force is equal to, work is equal to well, let me erase that again. That work is equal to a force times a distance, then you can see if D is equal to 0. 0 times anything means that no work was done. 0 work done. No work. However, if I did apply a force, okay, and you saw me push on it, and it did move a distance, then we had D no longer equal to 0. But now, because it moved, I can get rid of this, and whatever our force was, times our distance, was the work that we ended up with. So for now, let's say that I pushed with a force of 10, and you don't know what this is yet, but we'll learn about it, 10 newtons. And this is our force, and if it moved, a chair moved 10 meters, because meters we know is the units for a symbol distance. If I multiply those together, we had work equal to 100 joules. Now, look over this several times if you want. Let me go back. I want to add something to these notes of and definitions. I want to add that energy is measured in joules after the man who did all the work with work and energy. Now, those joules replace the actual units, which are kilograms meters squared per second squared. Put those in your notes. The units of work are also joules. And the units for work, that's the shorthand. You can also write that work is equal to kilograms meters squared per second squared again. So these are the units. This is the shorthand version of the units. And of course, the formula F and D are the symbols. Kinetic energy. guess what kinetic energy is measured in? First of all, kinetic energy, it says, is the ability, is energy in motion. Okay? And that's also measured in joules. All three of those are related. They're all measured in joules. And the units, again, are kilograms, meters per second squared. I'm going to prove that in a second. But just jot that down so far. You can pause this or rewind it and jot down what we've done so far. Now let me erase these for the time being, and then I'm going to go back. Erase all this so it's nice and clean. Let me see if I missed anything else on this. Alright, so we can already see that energy, work, kinetic energy, and potential energy for that matter, okay, potential energy is also measured in joules, and it has the same units. Okay, before we go on, force, we said in class, was the push or pull on an object. That was the definition of force. And gravity is an acceleration. Okay? It's an acceleration that pulls objects toward the center of larger masses. In the case of Earth's gravity, it's near the Earth's surface. That acceleration is equal to 9.8 meters per second squared. Okay, so these are our definitions. Just jot those down. Let me go on to the next page because I want to show you something here. We said that kinetic energy had a formula, and that formula was Ke was equal to 1/2 mv squared. Now, if you've already jotted down your units and your symbols, you know that m in a formula is mass. Okay, so I'm going to put that down over here, mass. And v is velocity. Okay, so our units, after we calculate whatever we have for potential energy, are going to be in kilograms, meters per second. Oh, but there's a squared over here, which means we got a square meters per second, which would give us meters squared over second squared. This is all we did. We took the meters per second, and if you square it, you're really multiplying it by itself. Meters per second, which equals meters squared per second squared. That's really all we did. And these are the units for kinetic energy. And as I said earlier, nobody wants to write all that, so oftentimes we use joules. So let me just write over here. Joules, let's see. Where's my pen? I just want to write down, I'll put it in honor of the man who did all the work with energy. So here are the units. Kilograms, meters per second squared, but oftentimes we just abbreviated joules. Now, the second formula, or the second formula for energy, is for potential energy. And that's equal to mass times gravity times height. Well, mass, again, here are the symbols. The SYMs are right over here. But the units are kilograms. Gravity is an acceleration. If you look at your chart for units and symbols, the units for gravity, same as an acceleration, are meters per second squared. And height is equal to the distance, so again, it's measured in meters. And again, when we multiply meters times meters, it's going to give you meters squared. So I can erase this meters, and you will notice that this these units are the same as these units. Well, we know there's a relation. Energy, by the way, cannot be created or destroyed. You know that. And certainly, potential energy and kinetic energy are related. They have the same units, for one thing. Now, we also talked about work. We said work is equal to a force times the distance. The force must be in the same direction as the object moves. Okay, so if you apply a force in this direction to a chair, there's a chair and there's a person. We'll better put a person sitting in it. There's a person sitting in the chair. This is the force applied. It must move some distance, d, for there to be work. Now, before I fill in the units for work, I want you to know that force is equal to a mass times an acceleration. And the units for force are kilograms meters per second squared. Okay. So if I move this guy in the chair out of the way, we know that in order to have work, we have to have some kind of distance. So over here, the units for force are going to be kilograms meters per second squared. And distance, of course, if you look at your chart of units and symbols, is measured in meters. Oh, wait a minute. Now we have meters per second squared times meters, and this gives us, meters times meters gives us, again, a meter squared, which means I can get rid of this meter over here because I just squared it. And once more, you can see that all these are related. Okay, as you can see, I put up the grid because I want to show you something about kinetic energy, the relationship of kinetic energy and potential energy. So let's just put over here kinetic energy versus potential energy. And I need the grid because I want to do some measurements. I'm going to pretend right now that there is a person right over here, and he's standing right there. Okay, here he is. And he's on a diving board. And that diving board, if this is the ground over here, this is the water. Matter of fact, I'll show it by drawing in a little water. Let's see, how can I draw this water real good? How about this nice pretty color over here? Okay, there's water all the way down here. Okay, is that nice water? Great. Now this person up on top, let's give him a little different look. Let's make him an orange. He's standing right there. There's his arms. And he is about to jump. There's his feet off the end of this diving board into the water. Now, let's say that he has a height of 15 meters. 5, 10, 15 meters. Okay, that's how high he is up in the air. Pretty high. And he's going to jump into this pool of water right down here. Now, is he moving right now? Well, first of all, let me tell you something. Total energy, let's call it TE, so I can save all this ink. Total energy is equal to kinetic plus potential. We're going to simplify it. There is no other heat loss in here. There's no friction or anything else. So total energy is equal to kinetic plus potential. Now up on top here, if he is not moving, how much kinetic energy does he have? Well, I would say that it's kinetic energy. I hope you answered this. his kinetic energy is equal to 0. But how much potential energy does he have? Well, let's see. We know that potential energy is equal to mass times gravity times height. And we know that right up here, his mass, I'm going to give him a mass of 100 kilograms, okay? So I'm going to say his mass equals 100 kilograms. So what's his potential energy? It's going to be equal to 100 kilograms. Notice the units. Gravity, I'm going to use for our gravity to simplify this. I'm going to say gravity is equal to not 9.8 but 10 meters per second squared, just to keep it simple. So this is their time sign right here, times 10 meters per second squared. And let's give him, and he has that height already of 15 meters here. Okay, so I put up the calculator here just so you can see that I'm not cheating and I'm really putting in these very simple numbers. You really don't need the calculator, but 100 times 10 times 15 is 15,000 joules. Now remember I said that we could, instead of writing all the units, well, I'll tell you what I'm going to do. I'm going to write all the units first, and then I'm going to simplify it. 15,000 is our answer. Kilograms meters squared per second squared, or 15,000 joules. And I can use a simple J for joules. Okay? So our total energy up here is going to, for this guy jumping off, he's going to jump all the way down to the water. Before he jumps, he is staying still. He has the potential energy equal to 15,000 joules. There's my J for joules. Okay? Now, I'm going to pretend he is right down here now. He jumps off and this guy is right next to the water here. Let's draw him just like this now. He's right over here. There's his head. There's his body. He turned from orange to pink, but that's okay. I'm not going to change it. Okay, so he's an inch away from the water now. Now, we know that his total energy, again, total energy is still equal to kinetic energy plus potential energy. Okay, but this time, potential energy, which is still equal to mass times gravity times height, his height is equal to 0. He's almost touching the ground. Therefore, potential energy must equal 0. So I'm going to write that down over here. PE, which used to be 15,000 joules, is now equal to 0. Now, since energy cannot be created or destroyed, it had to go somewhere. And don't forget, he is traveling pretty fast now before he hits. So could you make a guess as to what his kinetic energy must be? If the total, the TE up here, when I add these two together, if it must equal 15,000 here, it must also have to be equal to 15,000 down below. Well, that's going to make the kinetic energy, the moving energy, since he's now moving pretty fast, 15,000 joules, because energy cannot be created or destroyed. Well, let's see. What do you think the energy would be at exactly halfway? Okay, halfway in between. I'm gonna say it's about here. Let's see. I'm gonna say it's about here. Okay, we got 15, 7.5, right? 5, 6, 7, and right about here. Well, at this point, he's about half the distance. He's 7.5 meters up. So I'm going to guess that his potential energy, if you replace the 15 meters over here with 7.5, 15 meters right there with 7.5, you're going to have a potential energy equal to 7,500 joules halfway down. Well, we still have to equal 15,000, so where is the other energy at this point right there? What's the other energy, the kinetic? Well, that's going to be equal to 15,000 as well. I'm sorry, 7,500. Because the total, when you add these up, has got to equal 15,000. And you could pick any height along this whole thing, and if you multiply the potential energy, the total still must equal 15,000. And now his height is going down, so the potential energy is going down, but as PE goes down, KE for our diver is going up. Kind of get the idea here? Energy cannot be created or destroyed, only changed from one form to another.